screencast talks about spring force, Hooke's law, and elastic potential energy. Springs are objects that are used to store mechanical energy. Springs come in many different shapes and sizes, and they're used for many different things. You know, our automotive suspension systems, pendulum clocks, wind-up toys, watches, mouse traps, toys like the Slinkies. Here are some pictures of several types of springs, certainly not an exhaustive showing, but you can see that although the most common spring that we will discuss in our problems are coiled springs, like these at the upper left-hand corner. There are many varieties. Some springs are flat. There are leaf springs. There are disc springs, and so many different shapes. But when we talk about spring force, this is just a general description of the way that springs behave. So when no force is applied, the spring is relaxed and it is at its equilibrium position. If you look at the end of the spring when there is no force applied to it, that position of the end of the spring is called the equilibrium point. Then the spring can be either stretched or compressed. For example, in this picture on this slide, the man's hand is pulling the spring away from the wall. And so you can see where the zero is. That's where the spring would have been at equilibrium. But the end of the spring is now moved to the right by a distance x. And so it has been stretched. When the spring is either stretched or compressed, the spring applies a force to try to get back to its equilibrium position. And the force that the spring exerts, it depends on how far the spring has been deformed, either stretched or compressed, and also something called the spring constant, which has to do with how the spring is made. Hooke's law is the relationship that tells us how to find the spring force. Spring force equals negative K delta X. Here, the K represents the spring constant, which is measured in units of newtons per meter, and the delta X represents how far the end of the spring was moved, as the spring was either stretched or compressed. And that distance, delta X, is measured from the equilibrium point. The reason that this equation has a negative sign, right, spring force equals negative K times delta X, that negative sign indicates that the spring force is a restoring force. The spring is trying to return to its equilibrium position. At the equilibrium point, the delta X is 0. And so when you stretch a spring and pull the end to the right, the spring exerts a force pulling back to the left. If you were to push the spring to the left, the spring force would act and try to pull the end of the spring back to the right again. So that negative means that the spring force always acts in a direction opposite the direction of the delta X. So in this example, the man has pulled the spring to the right and has shifted the end of the spring by 0.36 meters. They're telling us that the spring constant, K, is 4.2 newtons per meter. And so if we want to calculate the force, we would use the equation spring force equals negative K delta X. So that would be negative 4.2 newtons per meter times the 0.36 meters. So the spring is exerting a force of 1.512 newtons back to the left. The spring force acts in the direction opposite to the direction that the spring was stretched. It's trying to return the end of the spring to its equilibrium position. Let's talk about the difference between the force that someone must apply to stretch the spring versus the force that the spring itself exerts to return to its equilibrium position. So the spring force, F sub s, refers to the force that the spring exerts, and that is calculated as negative kx. But the applied force, the force that someone must apply to either stretch or compress the spring, is the positive of that, is just kx. Notice there's no negative sign. These two forces are Newton's third law pairs. They are equal in magnitude but opposite in direction. So in this example, they're asking us, first of all, how much force would be required to stretch the spring 20 centimeters to the right. Well, here we're looking for the force that has to be applied to the spring. And so that is the applied force. So it would be K delta x, which would be the spring constant 4200 times 0.2. So someone would have to apply 840 newtons of force, pulling it toward the right in order to stretch the spring 20 centimeters to the right. As a result of being stretched, the spring is going to exert a force in the opposite direction. The spring force would be negative kx, and so it would be negative 840 newtons, or in other words, 840 newtons pulling to the left. So because the spring force is proportional to the displacement of the end of the spring, if no force is applied, the spring is not stretched, it's at equilibrium. But if you apply a force F, the spring is displaced by a distance x. If you want to displace the spring twice as far, so in other words, to a distance of 2x, you have to apply twice as much force. So there's a linear relationship between the force and the displacement. In this example, we have a 10 kilogram block hanging from a rope that's attached to a spring with a spring constant of 535 newtons per meter. The block has been allowed to hang and it has become stationary. It's come to rest. And now that it's at rest, we'd like to know what is the tension in the rope and what is the position of the end of the spring relative to its equilibrium point. We can see that the block has stretched the spring a little bit, right? It has pulled it down. So if we considered force diagrams for both the block and the spring, the block has a gravitational force pulling it down and a tension force pulling it upward, the tension of the rope. And the spring, actually, so I'm going to just fix this. This should be tension. The spring is feeling the tension of the rope, pulling it down, and then of course the spring force is pulling up in the opposite direction. So because the block is at rest, the net force on it is 0. We know that because of Newton's first law. Therefore, the tension force is balancing the gravitational force, and since it's a 10 kilogram block, 10 times 9.8 is 98 newtons. So we have found the tension force in the rope. It's 98 newtons. So now we also want to find the spring force. Now the spring is also stationary, and so the net force on the spring is also 0, that means that the spring force must equal the tension force, which is 98 newtons. And because we know the K, the spring constant, is 535, and we know the spring force is 98, we can solve for delta x. The spring must have been pulled 0.183 meters down, or in other words, the delta x is negative. It moved in the negative direction by 0.183 meters. When a spring is stretched or compressed, elastic potential energy is stored because the deformation of the spring, stretching it or compressing it, it's reversible. So the energy is stored until the force is removed and the spring is allowed to return back to its original shape. There are many objects that are designed to take advantage of this elastic potential energy. Things like a rubber band. You can stretch a rubber band. When you release it, it goes back to its original shape. The coiled spring of a wind-up toy or a wind-up clock. You wind the spring, and as the spring returns to its original position, you see the toy move or the clock moves. A bow and arrow, a diving board, a bouncy ball, a bungee cord. All of these objects are elastic, meaning that they can be deformed and then returned back to their original shape. Now, of course, there are objects like silly putty or chewing gum or things like that that can be deformed, but if they don't bounce back to their original shape, they are not storing elastic potential energy. So the ability to store elastic potential energy is very much dependent on a reversible deformation of an elastic object. So if we took a coiled spring, or any spring, and we, in this example, we're stretching the spring, we could do a graph of how much force it takes to stretch the spring to different amounts of displacement. The graph would be linear. The slope of this graph is the spring constant, K. And the area under this graph equals the amount of elastic potential energy that is stored in the spring. So the external force that is pulling the spring to stretch it is doing work on the spring, and that work transfers energy into the spring, causing elastic potential energy to be stored in it. The amount of the energy equals the area under the force displacement graph, and that area, notice it's triangular in shape, so the area is 1/2 times the height times the base, or 1/2 times the force times the displacement. But we know that the force required to stretch the spring equals K delta x, right, from Hooke's law. And so if we replace F with K delta x, we get a formula 1/2 K delta x squared. That is the formula to calculate the amount of elastic potential energy. 1/2 times the spring constant times the square of the displacement of the end of the spring.